Good afternoon. I'm Chris, and the other members of our group are Maya and Andoni. We're here to talk to you about our project, which was a renewable power station, for which Dr. Tremont advised us on. So our project consisted of two parts, a rain harvesting system and then an alternative energy storage system. The motivation behind our project was to reduce the global reliance on fossil fuels and also to provide access to the more than 500 million people that don't have access to energy nowadays. And finally, we also had a strong motivation to eliminate some of the toxic waste that comes with using electrochemical batteries. So these are some of the main alternatives that we had for the rain harvesting system. One was using a customized tank placed on top of the roof. And then another one was placing the tank on a base that was then attached to the column of the gazebo. We decided on the wooden base that was attached to the column with the tank on top. Part of the reason for this was that the other one with the customized tank on top, when it's full of water, then you have a lot of added weight on the roof, and then that reduces the factor of safety. And also, it made it more modular to have the tank where you could actually just add more tanks based on how many columns you wanted to use. For the energy storage system, we looked at using water, pumping it back up to the reservoir, or compressing air and storing that in tanks. We decided to go with compressing air because the other form of using water, it's usually used in dams, and they're usually hooked up to the power grid, and then when off-peak hours, they'll pump the water back up to the reservoir. But our system was designed specifically for off-grid use, so we don't really have access to a grid where we can use cheap electricity and pump that tank. And so these two systems will form part of an existing power station that Dr. Tremont already has, which already uses solar energy and wind energy. So we're adding rain, and then we're taking out the electrochemical batteries and substituting them with the compressed air system. This was the project timeline that we had. We had to improvise a little bit as time went along. And these are some of the things we had to think about when we went through the design process. Portable for us meant that it had to be able to be carried by two people, loaded on a truck, and then installed. And modular was basically that since it's supposed to be for developing countries anywhere in the world, different regions have different rainfall averages, so we had to be able to adapt to put on how many more tanks if there's more rainfall or less. SAFE basically looked at the gazebo, the structure, what we were adding to it, making sure that it has a good safety factor, that we're not making it a hazard for people. And the solid road simulations for this are on our final report. Low cost, since again we're developing this for rural areas in developing countries, we needed to use the most mass-produced parts that we could, because those are the cheapest ones. So when you use custom parts, that drives up the price. And lastly, we felt the duty to make it environmentally friendly, because in some of these rural areas, there's just really no way for people to dispose of toxic material like batteries properly. So sometimes they'll just chuck them out, and then it can end up in the water supply or something like that.
Okay, so now let's go into some numbers and equations we used to design the rain harvesting system. Okay, so the first thing we looked at was the amount of rain inches this region gets, so we can get a sense of what's the volume of rain we are dealing with. This is particularly important when we want to find how many tanks of water and what capacity they should be, right? So given the historic average of Miami and the patterns, we don't recommend that more than 8 tanks of 15 gallons are installed. As important as finding the volume of rain we're dealing with is also finding what is the rain intensity in inches per hour, so we can find a sense of the volumetric flow rate of rain we are dealing with. This is particularly important when we are designing the upper part of the gazebo, the gutters and the holes that convey all the water to the tanks, right? in order to design these holes in the gutters, we use marine equations, which helped us to find the average velocity of the rain flowing through the gutters. And knowing the volumetric flow rate from before, we were able to solve for the holes, the area of the holes. We found that only one hole at 3 inches per tank is more than enough to cover most situations. Okay, so moving down the design process, we needed to find the velocity and the pressure at which the water hits the turbine. So in order to do that, we created a control volume from the bottom of the tank to the top of the turbine. And we, using Bernoulli's equation and Darcy-Weisbach equation, we were able to solve for these two unknowns for 4 different pipe diameters, so we could compare. Finally, for some power calculations, it is important saying that the actual turbine that is going to work with the system isn't ready yet. So we needed to use a model whose properties are unknown. For that reason, we needed to make an educated guess on the head of that turbine in order to find the power. So we assumed that the head of the turbine is 9 feet, which is roughly 3 meters. And once we assumed that, we were able to find the power generation for 4 different pipe diameters, as you can see on the table. Okay, so now Tony is going to talk about the other system.
About the alternative storage system. Here, this table, we have the inlet and outlet state properties of the air tank. The important information, the most important information on this table is the enthalpy. Because with that enthalpy, later on we'll calculate the energy that we can store in the air tanks. This table presents the properties of the tank itself, which includes the release velocity and the volume flow rate that the tank can develop for this specific valve size. Using the 2 previous tables and these 2 equations, we were able to calculate the amount of power, the amount of energy that we can store in both the battery banks and our alternative system. We have to mention that these calculations were assuming that only one air tank was installed on our system. But that number, that capacity can increase significantly if we install more than one tank. Now I'm going to present the cost analysis for the system. This table presents the cost and the life of the components needed to install the rain harvester system. Using the information in the previous table and assuming that the system will work for at least 7 years without any major maintenance, we determined that the price of what produced in our system is $0.0014. Even though that price is greater than the price that a regular person pays here in Florida, we have to remark that this system is for a rural location, so this price is fairly good. Now this table presents the cost and the life of the components required to install the alternative storage energy system. As we can see from this table, the life of the components that we're using for the alternative system is much greater than the one that they use on the battery bank, because we know that we have to change battery more often. So in the long term, the alternative system performs the both performance equally.
Okay, so for the prototype testing, we wanted to build both systems here at FIU, but because of some paperwork issues, we needed to find an alternative, and we ended up building both prototypes at a friend's house. Okay, but however, that's the only difference between both the original plan and the one we actually executed, because all the components and parameters are the same. In the particular case of the rain harvesting system, the tank is the same capacity, the height is the same, so it should perform the same. Okay, so since we couldn't bring the prototype because of the size, we decided to create a video so you guys can see how everything works. So going into the major components, we have, of course, the water tank, which is 15 gallons. It is on a wooden base at 4 feet height. Then we have the valve to control the flow of water. Then moving to the bottom, we have a T with a turbine, and then the shaft going out to the gearing system. This is how everything looks. Okay, now you can see a video of how everything works basically. You let the water go through, it spins the turbine, and then power is transferred through the gearing system. Looks nice. So, the beauty of having gearing systems is that we can set up different ratios to play with the velocity and the torque, right? So here we are showing a 1:4 ratio. So as you can see, it's extremely fast. You're looking at 1200 RPMs average. And even in the slow motion, you can barely tell what the nail is. And then we decided to show the opposite, which is a 4-to-1 ratio for slower RPMs but more torque. And this is the results we got from the testings, okay? So we have RPMs for 3 different gear ratios. As you can see, the system can perform from anywhere 60 RPMs, generating theoretical 25 watts, to 1200 RPMs, theoretically 400 watts. Going into the following prototype, we pretty much did the same thing. Okay, we put all the components together and we set up a GoPro camera to record the output shaft at 120 frames per second. Right? Again, we couldn't bring it, so we prepared the video of how everything works. These are the major components of the system. Of course, we have a compressor, a pressurized air tank of 6 gallons, 150 psi. It is connected. Then we have a diffuser that we use to increase the efficiency of the turbine itself, of course. Then we also have a shaft, an output shaft. This is an overview of how everything is connected. You have the compressor and the air tank is a single module. Then you have an air hose, and then the turbine is fixed to that base, so it stays in place. We also attached a nail to the output shaft, so it is easier for us to record the RPMs, right? And this is how everything works. You have here the pressure gauge. So you open the valve, air goes out, and it spins the turbine, right? As you can see, it spins really fast. I mean, even in slow motion, you can tell. And then notice that for this one, we don't have a gearing system, so this is a 1-to-1 ratio pretty much. Okay, so for the results we got, we did this trial several times, and we find that the average RPMs of the system is about 453 RPMs, which is like considerable, especially if you were to compare this with the previous system. For a 1-to-1, this is almost twice as much. So we're happy about it. And this concludes the testing. So now Chris is going to speak about standards.
These are some of the standards that were used by the manufacturers of our water tank and air compressor. All the ones that you see that are ASTM are for the water tank, and the UL one is for the air compressor. The essential parts of each ASTM standard is on the Appendix C of our final report.
All right, in order to make our system more efficient, several things can be done. For example, we can increase the size of the air tank or the pressure that it can hold, so we can store more energy in that tank. Another possibility is to increase the size of the water tank and the altitude where it's placed, so we can store more potential energy that can be translated into electrical power. Also, we can include a variable gear transmission, so we can play with different generators and work and get the most power out of them. Before concluding our presentation, I want to remark that the purpose of the system is to produce green energy to a more remote and rural location. So if these two systems work together with the already existing solar panels or windmill, we can produce a decent amount of energy throughout the whole year and throughout every climate condition, or almost every climate condition. Also, we can reduce the chemical waste attached to the usage of electrochemical batteries, and we can reduce the usage of fossil fuel. This concludes our presentation. However, I want to give special thanks to Dr. Andres Termante, Dr. Sabri Tosunoglu, Uber Mantovani, John Butcher, and Mr. Pradeep Shen. Thank you very much. Any questions?
Comments?
I noticed with your compressed air, you basically showed that you had, what, 26 seconds worth of
Yes.
compressed air that you were generating all the energy in. For your water flow rate, was there something similar on?
It was 10 seconds.
10 seconds. So my question becomes, can you generate enough power in those 36 seconds to last until the next time those are refilled?
Well,
Right. The purpose of the prototype is to show that the system works. As we said before, this system is modular. So if we collect the water on 8, 7, 6, 4, 3 tanks, we have more time to release that flow rate and to produce more energy. The same with the air tank. In the prototype, we use a 6-gallon air tank. But for our calculation, we use a 4 meter cube airtime, which is a lot bigger.
Yeah.
And that difference is significant.
You can increase, and also you can like, how can you say, you can like optimize the system for each task. For instance, let's say here in Miami it's no rainforest by any means, so we don't have as much water, maybe in another place in another country. So, well, we theoretically we are generating maybe 400 watts if we go with that gearing transmission. So what you can do is when you are starting an appliance, they make a peak power, right, which is like 6 times maybe as high as them, and then it still rises. So maybe you can optimize the system to only run while that appliance is starting, and after that you can reserve that energy in a smart way, yeah. And you can rely more on sun and wind.
But what I see that it's very finite, it's, you have to wait for rain and then you get a few minutes of power and,
Yeah.
I mean, how much savings are you really getting out of that from the cost perspective,
As I've given in the cost analysis, if we produce that theoretical power that that we want, we produce in a fairly cheap kilowatt hour. I know that the system runs really fast because we're doing the prototype with a 15-gallon water tank, which is not the optimal size for the tank. But since we don't have,
What would be the optimal size of the tank?
I declared at the beginning that, no more here in Miami, no more than 8 tanks of 15 gallons.
so
Because what we have is 43 gallons on average, per month, but we know that doesn't happen that way, right? We have like maybe 2 months of rain, and then like the rest is like pretty much dry. So yeah, during that time you're collecting that water.
Right. I mean, I think we share the same concern then. If you're still 10 seconds a tank,
Yeah,
you're looking
I mean,
at 80 seconds of generation that way.
a month or a week or something.
You're talking about watts, right? I mean,
yeah, but
run a home or
Yeah.
even a TV for
No, I know,
about 80 kilowatts.
Watch TV for
Yeah,
8 seconds,
yeah. I mean, we pay 8 cents per kilowatt
That's not
hour or
it?
something.
That's-
from it.
yeah, but
Yeah.
as Maya said before, there are some appliances, for example, compressors. They have a peak when they turn.
Oh, yeah, yeah.
So you can use that amount of energy that you have to break that peak.
No.
And then when the system stabilizes, you can rely on the other components that you have.
Oh, as an example, I like it.
Because
What is
there's
it
also
for?
solar and wind energy added to this, so.
Right, right,
you
yeah,
can
no,
do
no,
it
it was
together.
Excuse me.
Right.
Anything?
All right, that was it for me.
And also on your comment about the savings, this isn't really meant to do energy savings per se, because people, if you have access to the grid, it's a lot cheaper to just connect to the grid.
No, I didn't mean it like
This is-
that type of savings. I meant the capital investment part of it,
Yeah.
for your return on your investment.
Yeah, I mean, as we
Cost
mentioned many
benefit.
times, this is for rural
The
places
ROI.
where you don't have the power to, we won't feed the whole house, but we can maybe feed a small room, for example, with a 2 extra components, of course.
Also, another thing is we are showing the testing results for a 2 inches pipe diameter. If you reduce the pipe diameter, you're gonna have more time producing energy, you're gonna have less.
Energy.
So you're also gonna be storing that electricity with batteries, right? Is that what you
Yeah,
said?
with the compressor tank.
Compressed air.
Compressed
Oh,
air.
compressed
Yeah,
air.
the compressor.
And the compressor then turn it.
Yeah.
If you have to do it all over again, if you have any restrictions, cost restrictions, etc., what would you do different?
What would I do different?
I think that, one of the most important components that we wanted to add was a variable gear system. Because in that way, you can set up your system for any generator, for different generators. So you can, for example, you have a cheap generator, you can modify your system to output more torque so you can run it. You have a better generator that requires less torque and produce more energy. You can change your system to produce less torque but more speed.
I would also include a nozzle in the pipe diameter, so we increase the pressure going to the turbine, and that way you are prolonging more the amount of water you have, the time you're producing energy, and also you're increasing the efficiency of the turbine.
So did you calculate how much water you need for X amount of time for power of a light bulb, for example?
Well, we have like,
We didn't have the money, for example, to buy the generator.
Yeah.
For example,
we couldn't like
So
include
we we couldn't test how much electricity do we produce.
So just really quick, sorry, one more time. In a month, how much power can you estimate you can generate?
For example, if we have 43 gallons, it means that you fill each tank 3 times.
3 times.
So 1,200 watts, something like that?
No,
No?
not even close.
Not even close, right? So if I have a 60-watt light bulb, how long can I power that using this system?
16 volts.
60 watt, right? 60 watt.
We're producing 400 times 3.
I mean, only using the system.
Right.
Because remember, we are.
It's fine.
Right.
We're saying what was the benefit, that's what
Yeah,
we're
right.
saying, yeah.
But anyway, it's fine. So just, can I make one comment? Sorry, this is a real bad pet peeve of mine, and you two I'm very mad at, right? All of your numbers in this entire thing are 9 significant digits long. And I can't tell you how many times the two of you I've said, don't make 9 significant digits, right? So if you go back, it's a pet peeve, I know it's a nitpick, right? But I don't know how many times I've said this to you two in general. Keep going back, keep going
No,
back.
I think there's only one number that.
There's only one. Oh, Adoni, now you're in trouble. Adoni. There's only one. Look, keep going back. Keep going back. There's one with 9 significant digits. Boom, right there. 103. Come on, man. Come on, Adoni. You're in trouble. Keep going back. I'll show you 10 of them. There's, oh, come on. What is this? What is this? I know, this is making me so mad. I couldn't even pay attention to half of this because of these numbers. Look, every single one of them. Oh my gosh.
They're making sure you pay attention every move you will see.
9 significant digits. You're telling me that's focus, man. You're telling me angstroms in terms of meters, right? You're telling me that's number. Anyway.